So in part 1, we have derived the moment equations for M1. M1 is for the beam segment AB. M2 is for beam segment BC. Okay. So in these coordination systems, so for beam segment AB, we have x is larger than 0, less than 2a. So this is beam segment AB. For beam segment BC, x larger than 2a, less than 3a. Okay, so this is two bending moment equations. Once we have bending moment equations, then we can apply these elastic beam theories. So we need to determine the displacement at the point C. So C at the point C, x equal to 3a. So x equal to 3a is point C. X equal to 3a. This is point C. So that means the point C is on the beam segment BC. So BC, that is M2. So first of all, we need to evaluate D square. So it's Y2 equal to M2. So M2 is equal to Px 3Pa. So this is for x larger than 2a, less than 3a. Okay. So first integration on both sides we will have EI dy over dx equal to 1 over 2 px squared minus 3pax plus the constant c1. Second integration, we will have 1 over 6 px cubed 3 over 2 pa x squared c1x plus c2. So we have two unknown constants, c1 and c2. So we need to apply the boundary conditions. So boundary conditions. So for boundary conditions, look at the beam here. For boundary condition that at support B, the displacement equal to 0. So we can only have one boundary condition. That means that is support B, x to 2a, y2 equal to 0. So we only have one boundary conditions. For this one boundary conditions, we just come out, we cannot solve C1 and C2. That means we need other equations to help us to solve these two unknown constants. So that means just by this equation, we cannot solve the y2. So then we need to look at M1. So look at M1, that is x larger than 0. So on the beam segment AB, we have EI dy1 dx squared equal to M1. So M1 is equal to here minus 1 over 2 px. So 1 over 2 px. By double integration, we have EI dx equal to plus constant C4, and second integration we have y1 equal to 12 px cubed plus 33x plus C4. Okay, we have two more unknown constants, C3, C4, but for this beam, we have two boundary conditions. For at support A, x equal to 0, y1 equal to 0. Support B, x equal to 2a, y1 equal to 0. We have two boundary conditions. So these two boundary conditions can help us to solve C3 and C4. But so we need two other conditions to help us to solve. So boundary condition here. So x equal to 0, y1 equal to 0, x equal to 2a, y1 equal to 0. So we have three boundary conditions, but we have four unknown constants. So now we need to other conditions. That conditions we have introduced in the lecture, that is continuity condition. So continuity condition is that. So look at this deformed shape. That's this deformed shape. So this deformation, this is continuous at support B. That is mean the displacements must be the same. They are all 0, so it's same. And at support B, the slope must be the same. So the slope, we come out two slope. So one slope is from y1, so is y1 x. So this is fourth slope at x equal to a. This is on the beam curve AB. On the beam curve BC, we have the other slope is dy2 equal over dx at x2a. So these two slopes must be the same. This is continuity conditions. So continuity conditions. So now we have four. We come from the boundary conditions and continuity conditions. We can write down four equations. So then four equations and four unknown constants, C1, C2, C3, C4. Then we can calculate these four unknown constants. So let's write down these four equations. So first of all, at boundary condition 2a, we will have the first equation is, let's write down here, px 2a cubed 3 over 2 pa 2a 2 plus c1 2a plus c2 equals 0. So this is first equation. Over here, x equals 0, y1 equals 0. So we have y1 equals 0 equal to x equals 0. That's c4 equals 0. And then from this boundary condition, x1 equals 0 is equal to 1 over 12 p times 2a cubed 3 2a plus c4. So c4 is 0, so it's 0. Can cancel it. So this is two equations. And then the fourth equation is shown here. Fourth equation. So first of all is dy1 over dx. X equal, so at x equal to 2a, this slope is expressed. So this slope is expressed here. So we have, so x equal to 2a, we have 1 over 4 p 2a square plus c3. So this is slope at x equal to 2a. So we can write down here. So 1 over 4 p 2a square plus c3. This is on the left hand side of this equation. And the other part of this equation is dy2 over dx at x equal to a. So it's showing here. So x equal to 2a, we have 1 over 2 p 2a square minus 3 pa times 2a times c1. Okay, so this, if we write down here, put this over here, we will have 1 over 2 p 2a square minus 3 pa times 2a plus, so plus c1. Okay, so we don't consider EI on this here because the EI are same, so we don't consider here. So now we have four equations: equation 1, equation 2, equation 3, and equation 4. So based on these four equations, we can come out four unknown constants. So now we come on for the constant value will be, so we know C4 equals 0, and C3 can be calculated is 1 over 3 pa square, and C1 is 10 over 3 p square and C2 is equal to minus 2PA cubed. Okay, C1, C2, C3, C4. So after we plug in C1 and C2, so now for the beam segment BC, the equation will be so for the BC segment, the deflection equation will be y will be 1 over EI times over here. So it's showing here. So 1 over 6 px cubed, 1 over 6 px cubed negative 3 over 2 pax squared, 3 over 2 pax squared, and plus c1x, so plus c1x plus c2. C2 is showing here, so c2 is here, negative pa. Okay, so this beam segment, so we plug in x equal to 3a, then we can come out delta c. Okay, so if we plug in x equal to 3a into this equation, we come out delta c is equal to negative pa 3 pa cubed to EI. So this is the final result for the displacement at point A. So the idea is quite straightforward, but it takes a while to come out these equations by using double integration method. So first of all, we come out the equation of equation for the bending moments. We need two equations, one for AB and the other one for BC. So we have M1 and M2. After we have M1 and M2, we apply this equation. We do double integration on these two equations, first on M2, then on M1, then on M1. So we have 4 unknown constants, but we only have 3 boundary conditions. Then we need that means we need to apply actual equation. That actual equation is come out from the continuity conditions. So the continuity condition is that at the point B, there's no break. So this deformed curve is continuous. So this deformed curve is continuous. That means the displacement is same and the slope is same. So the displacement is 0 for both curve, and the slope must be equal to each other. So that means we can, based on this continuity condition, to come out one extra function is shown here. So the slope from y1, slope from y2 at the same location is equal to each other. So we come out this extra equation. So now we have 4 equations, 3 of them from boundary condition and 1 from continuity condition, and then we can come out the 4 unknown constants. The constant come out, then we can derive the displacement function. So it's shown here. So then based on this displacement function, we can come out the displacement at point C, x equal to 3a. So after some calculation, I can determine the delta c is equal to this value. So that's all.